above. Star.
All right, let's go ahead and get started. So we've talked about different types of parallelism, instruction parallelism and data parallelism. Instruction parallelism where you try and run multiple instructions, you try to run multiple instructions at the same time, or at least multiple pieces of the instructions at the same time. And that was done with our in-order pipeline as well as our out-of-order pipeline. The next type we went through was called data parallelism, where you'd have one instruction that would operate on multiple pieces of data at the same time. The next level, so to speak, is thread level parallelism, where you'll have multiple threads of execution. You think of this as multiple processes trying to execute simultaneously, and you have to, of course, have multiprocessors or multi-core in order to do this. This, unfortunately, is the most complicated one. It's going to have a lot of issues, but unfortunately, we kind of run out of ideas of how else to speed up our processors. So this is pretty much what's left.
Flamey stickers?
Yeah, I've thought of. Someone did bring that up. You could just put flames on the side of your CPU; it'd go faster, right?
But that gets way hotter too.
Yeah, well, then you just put liquid cooling, right? All right. So have multiple program counters. This is MIMD. If you remember, data parallelism was thought up as SIMD, single instruction, multiple data. Now you have multiple instructions acting on multiple pieces of data. Usually you want to target for tightly coupled shared memory multiprocessors, although that's not always the case, because sometimes you will have a program that, y'all did SETI at home? That whole thing where it searched for alien life for all the information coming in. Do you remember that?
Oh yeah, when you take a telescope and you stare at the sun and it really hurts.
Yeah, that's not it at all, but that's okay. That one was they sent packets out and had your computer process it and then come back. That would be not so much tightly coupled shared memory. That would be not.
Yeah, that's on the communist side of things.
It is on the communist side of things, yeah. But tightly coupled would be, we're still on one processor, so think of just multi-core, but still on one chip. So if you have N processors, you need N threads. The amount of computation assigned to each thread is what's thought of as the grain size. So this is fine grain or coarse grain. One thing to keep in mind is they can be used for data level parallelism, but the overhead may outweigh the benefit. Have any of y'all done thread programming before a bunch?
Tons.
You did it in OS. So the thing about threads is you have to create the thread, set it up, and then fork it or make it go. So there's a lot of overhead to set up the threads and have it go, and then there might be a lot of communication problems in between, not just programmatically, but we'll also find out also in the hardware, and that could slow it down, and it may not be beneficial in certain situations. When it comes down to it, if you can use SIMD instructions instead of thread level parallelism, just do it. You'll get a lot better performance out of it, at least for now. All right, so you have symmetric multiprocessors, small number of cores, share a single piece of data. That's up on top. The idea is you have multiple processes. It might have its cache, but it shares a piece of memory. And then distributed shared memory. Everyone has their own piece of memory, and they somehow communicate over some type of network, aka a lot of computers on the internet. What's happening inside of one machine? Oh yeah, some other terms: non-uniform memory access / latency. Definitely happens here because all these machines are different processors, different architectures, so the memory may behave differently, different performance. Up here, this can happen as well, although not as much. And let's see, connected via switched or a multi-hop interconnect networks for your distributed. All right, you see the difference? Matt, when would we use one over another? Ooh, here we go.
Now, if you've got a shape that's not symmetric, you won't want to use the symmetric one.
Okay. I need to remember not to ask Matt questions. That's how it gets you. So the SETI at home, they probably have something else by now, don't they? They have some program, let me use your processing cycles.
Bitcoin?
Bitcoin? Oh yeah, Bitcoin. Yeah, that's definitely this one. Yep. Well, if your program is using multiple threads, which actually most games do nowadays.
I always think of Google when you look at that bottom one, their warehouse of
Yeah.
inexpensive servers.
Yep. Yeah, it's definitely the bottom one. Okay. Cache coherence. All right. Processors may see different values through their caches. Let's see. So over here you're having time. We're just doing time units. Any time units. You can think of a millisecond if it helps. Processor reads X, reads some value, puts it in the cache, and knows that that value is also in memory. Processor B reads that value. All right, it has it as well. Processor A stores 0 and X, so it has 0 here, and then maybe if you're doing a write-through cache, it would go to this memory, but processor B's memory hasn't been updated because he hasn't been accessed yet. Is that a problem? Does processor B have the right piece of information is the question. If it tries to read the value X, it's going to give back 1, even though the real value is now 0.
Oh no.
That's the issue. Do y'all see that problem there? Did we get so far? Jordan?
No.
No? So think of these as different time steps. So initially, none of the processors have done anything. The value of X is 1. It's stored inside of main memory as 1. Processor A tries to read X. It's still 1 in main memory. It puts 1 inside of its cache so it can access it quickly later. That happens in 1. Afterwards, processor B reads X, so it reads it from main memory, puts it inside its cache, it's 1. So both A and B have the value of X in their cache with the value of 1. A decides to write to the value of X, store it. So he writes 0 to X, puts 0 in his cache, because that's what it is. Goes ahead and writes out the main memory. But B is not updated. So B, if B were to read X right here at step 4, it would get back 1, which is not correct.
Okay.
We good, Bart?
Yes.
All right. So coherences is all reads by any processor must return the most recently written value. That's basically it. Writes to the same location by any two processors or seen the same order by all processors. Basically, everyone has the right values when they try and read from it. Consistency is a little different. When a value is written will be returned by a read. When a written value will be returned by a read. If the processor writes, wait, how does this work? Location A followed by location B. Any processor that sees the new value B must also see the new value of A. Right. Okay, that's just keeping. If a processor writes location A followed by location B, any processor that sees the new value of B must also see the new value of A. In other words, think of it as a sequential line. You're not jumping around
It
reading.
has to be in order.
Yeah, it's in order. The coherence ends up being, well, the consistency is important. The coherence is the bigger problem. All right, so with coherent caches, you have to migrate movement of data. In the previous example, B's cache, you need to do something with the value of X in there, either update it with the correct value or invalidate it. Or you need to, migrate it, move the data. That would be invalidate everyone's data, or you can replicate it. Make sure you update everyone's X values. In other words, if A was going to write to X, migrating would invalidate B's value, and then it could write to it. So it migrated ownership to A's cache, in which case this value would be invalidate right here, and that way if B tried to read, it would know it's invalid and have to get back from memory, and then it would get the correct memory. Replication would be if A wrote to X, when it hit main memory, it would also update B as well. So that's the main difference here. It's really your two options.
Is one more costly than the other?
That is a great question. The answer is it depends. And we're gonna delve into cache coherence a lot more I just want to go through the book slides because I think it gives a good overview before we go into the slides I put together. Cache coherence protocols, there's 2 of them. Snooping, let's talk about that one first. Each core tracks sharing status of each block so it knows what the sharing is. For example, at this point, A knows that it owns X because no one else has it, so it can do whatever it wants. But when B reads, then it knows it must be sharing it with someone. Then what happens when you write to it, you would either take ownership by invalidating, or it would be, take exclusive ownership, I should say, by invalidating it, or it would be a shared ownership thing if it was updating the other one. And we'll get to that in a bit, but I want to show you there's a lot of states to cache coherency. And snooping is each cache takes care of it. Directory base, basically main memory tries to keep track of where everything is. Oh, are we going to go through all of them? Okay, sweet. All right, cache coherence, write and validate. On write, invalidate everyone's caches, so that's what I was talking about here. With our previous example, notice now X has a value of 0. A reads it, we're good. B reads it, we're still good. A tries to write 1, it invalidates X, so he no longer has it. And then B tries to read X, it's a miss, and has to go to main memory. You see what's happening? Right. In a write-back cache, the updated value must be sent to the requesting processor. Cache lines marked as shared or exclusive modified. We'll get a little more into that in a moment. Oh my goodness. We're skipping that. Oh, here we go. We're going to see this again, but let's look at it now. This is... I don't like this picture at all. Oh well. Sure, exclusive. This is usually the very basic snooping cache coherence protocol. Is you have 3 states for every cache line. Invalid means that there's nothing validly written there, so you can overwrite it. Exclusive means that you're the only one that has access to it right now, so you feel free to read and write to it. And then shared means that someone else has a value of it as well in their cache. Feel free to read from it, but if you write to it, we're going to have to do something. So those are the main situations. Usually the way this goes is you invalidate, you want to read, you make a read, it replaces an invalid cache line and sets it to shared. So you keep reading it, you can keep reading and it'll still stay shared, right? There's no big deal right there. If you decide to write to it, or you're invalidating and you decide to write to it, you have to go to exclusive, which means you tell every other processor, invalidate your cache, I'm going to be exclusively own this. And then you're allowed to write and you're allowed to read to it as much as you want. If someone says, hey, I need a copy of it, then you're going to have to send that copy out, go back to shared because someone else is reading from it. And then again, you can start from there as well.
So when they write to it, it goes to invalid.
Yeah, they don't show this here, but yeah, if someone else writes to it, you have to go back to invalid.
Shame on them.
Yeah.
Did you see this before though?
What's
or
that?
A similar diagram.
Yeah, we'll see this again.
No, I mean, didn't we see it before?
I thought so. I thought I went over this, but
I thought you.
okay. Oh well.
Maybe.
Yeah, this is the MSI protocol because exclusive is really modified. These slides are being confusing. Let's see. Operations are not atomic. You have to detect a miss, acquire the bus, receive a response. So there might be some deadlock or erase conditions. How could that happen? Well, what if your 2 caches were shared and you both tried to write to it?
Sadness.
Sadness occurs. So there has to be some type of logic in order to say, okay, this processor is allowed to do the write and not that one. You're going back to invalidate and you're just going to have to wait for a while.
Which one? How does it determine which one?
I'm sorry, say again?
How does it determine which processor?
Whatever the designers decide. Because if they both came in at the same time, you can't use time. If it was me, I'd just processor 0 has the highest priority.
Oh.
That's the way I would do it, make it simple. You can always extend this. You could have exclusive state indicate a clean block and only one cache. We'll go more into this in a bit. And that's it for that one.
Bye.
What?
Bye.
You want to leave already? That's nice.
That was a good lesson.
That was a good lesson. What did you learn?
Snoopy.